Welcome to Deep Dive Dialogues, the show where we make the impossible possible, one question at a time. I'm your host, Isabel, and today we are tackling something that sounds like it came straight out of a sci-fi novel. But it's actually a paper, a real, live academic paper. And to help me unpack it, I have two of the sharpest minds I know. First up, the man who can explain a transformer model using a recipe for bibimbap, JJ.
Ko inyong hasyoinus, Isabel, always a pleasure. And I promise no bibimbap analogies today. Maybe we'll see.
I'm holding you to that. And also with us, the person who asks the questions that make everyone in the room stop and think, Yong.
Do it, let's get into it. I've already got about 12 questions just from the title.
Channel everyone. So the paper is called ADEMA, a knowledge state orchestration architecture for long-horizon knowledge synthesis with LLMAgents. And I'll be honest, the first time I read that, my brain did a little glitch. So JJ, let's start with the big picture. What's the problem ADEMA is trying to solve?
Right, so imagine you're building a very complex Lego castle. You have 1,000 pieces and you're working on it over several days. The problem is, if you leave the table for a snack, you might forget which wall you were working on, or you might accidentally build the tower on the wrong base. That's what happens with long-horizon tasks for LLMs. They don't have a good memory of what they've already decided or what pieces they've already placed. Their knowledge state drifts.
So it's not that they can't answer a single question. It's that they can't keep track of the whole conversation across many steps.
Exactly. The paper calls this knowledge state drift. And ADEMA is an architecture designed to fix that. It's like giving the LLM a notebook, a project manager, and a backup plan.
But let's be precise. The paper is very careful to say this isn't just another multi-agent system, it's an orchestration architecture. The key contribution is the explicit epistemic bookkeeping. They're not just passing messages between agents, they're tracking what the system knows and what it doesn't know at every single step. That's a huge shift.
That's a great point, Yong. So it's not just about getting the right answer, it's about understanding the asterisk path to the answer. And the paper mentions a dual evaluator governance system. What does that mean?
Think of it like having two editors. One editor is very strict about facts and logic. The other editor is more concerned with the overall story and whether the final answer makes sense in context. They work together to keep the system on track. The paper shows that this dual evaluation is a supporting control mechanism that shapes the trajectory, rather than being a simple yes-no check.
And it's not a universal requirement. The paper's mechanism matrix is really clever. They ran 60 fixed experiments, and the only thing that caused a complete failure was removing the checkpoint resume capability. That's the backup plan JJ mentioned. If the system gets interrupted, it can pick up exactly where it left off. Without that, it's like trying to finish the Lego castle after someone kicked the table.
Wow, so the most critical thing is just being able to save your progress. That's almost too simple.
It is simple, but it's profound, because it's not just saving a text file. It's saving the entire knowledge state, the artifacts, the evidence chains, the intermediate commitments. That's the artifact-first assembly and segment-level memory condensation the paper talks about. They compress the important information so it can be resumed efficiently.
Okay, I think I'm starting to see the latter here. We start with the problem of forgetting. Then we add a notebook, epistemic bookkeeping. Then we add editor's dual evaluation. And finally, we add a save button, checkpoint resume. And the paper's evidence shows that the save button is the most important piece.
Exactly, and the paper is very honest about its limitations. The evidence is drawn from a 4-scenario showcase package and a fixed 60-run mechanism matrix. They also did targeted microablation to isolate specific effects. It's a very rigorous, well-scoped study. They're not claiming this is the final answer for all AI problems. They're saying, here is an architecture where explicit state tracking, artifact progression, and recoverable continuity are the primary design commitments.
So the takeaway for our viewers, if you're building an AI system that needs to do complex, long-term tasks, don't just throw more models at it. Think about how you track its knowledge. Think about how it recovers from interruptions. Think about the architecture of its memory. That's the ADEMA contribution.
And remember, it's not about making a perfect AI. It's about making an AI that can gracefully handle the messiness of the real world. Interruptions happen, mistakes happen. The question is, can the system recover?
Well said, it's a realistic, practical, and deeply thoughtful piece of engineering. And it gives me a little bit of hope that we're moving past the bigger is better phase and into the smarter is better phase.
I love that. Smarter, not just bigger. Thank you both so much for this incredible breakdown. And thank you, our viewers, for joining us on this journey. If you want to dive deeper into the paper, the link is in the description. Until next time, keep asking those sharp questions. From all of us, thank you.